All right, so we're going to turn our attention to bolted joints in shear. This is another question about a trailer hitch. Instead of the bolts being arranged such that they're screwing into the trailer along the axis of the coupler in this direction, these bolts are arranged sideways. So they are going to be under shear load as opposed to a tensile load. So our problem is to find the maximum force along the axis of the coupler, so along this axis here, along this axis, that the bolted joint can support. So we'd have a load along the axis here, and we're asking what sort of force in that direction can this bolted joint support. Here's a diagram that I've drawn from a few sides. So I'm going to move this up so we can see them at the same time. So this here is a side view as viewed from the side over here. It's 4 inches tall, so 4 inches. The holes are clearance holes for 1/2 inch diameter bolts. So they are 17/32 in diameter. There's 2 of them. The distance to the edge, from the center of the hole to the edge, so from the center of the hole to this edge here, or the center of is 3/4 of an inch. And these plates here, they're 3/8 of an inch. I'm assuming that the steel plate here, this bracket, is made out of AZ1018, which has a yield strength of 32 KSI. And it says in the installation manual that these are SAE grade 5 bolts, which has a yield strength, not a proof strength, but a yield strength of 92 KSI. So when we're looking for the material, when we're analyzing for shear, we're going to be analyzing with yield as the criterion of failure. And so I'm using 1018 steel. Hot rolled yield strength is 32 KSI. And the yield strength of a grade 5 bolt is 92 KSI. Note, I'm not going to use the proof strength here. I am analyzing for shear. We say that bolted joints in tension, we're going to use the proof strength. Bolted joints in shear, we're going to use the yield strength. And we're going to assume that the threads of the bolt are not in the shear plane. So I guess the best way to see it is from this point of view. At these interfaces, this is where if you were to cut the bolts kind of at this location, right, something really sharp in there, and you were to shove it in there and that was going to cut the bolts, that's the shear plane that I'm talking about. So we're assuming there's no threads there. We're going to make sure that the unthreaded portion of the bolt extends from the head of the bolt through the end of the bracket, but then somewhere in the middle of these holes is the run out where the unthreaded portion goes to the threaded portion so that these nuts can screw right onto the threads. Okay, so we're assuming that the threads are not in the shear plane. We can use the full diameter of the bolt, major diameter, to calculate the area it's going to shear over. What's the maximum force that the bolted joint can support? And I say that it's along the long axis of the coupler, not just to mention the direction of the load, to disambiguate from a load that might act upwards. That would be like the tongue weight of the trailer pushing upwards on it. We're not going to consider that. But also, I mean that it's going to be centered with respect to these holes. We don't have to consider any effects due to bending moments that need to be supported by these things. We can assume that they're all in pure shear and that whatever the total force is, it's divided equally among all the different locations. So here's the different ways from Shigley. This is a really important diagram for analyzing. This is showing just a single bolt in shear right here. This is showing several different ways that the joint can fail. The joint could fail due to bending moments in the bolt or the rivet, because we're going to analyze bolts just the same way as we would rivets. In this case, we're not going to have this sort of thing happening because we've got symmetry on our side. We've got 2 places that we're pulling on. You're just not going to end up with these moment loads. So we can ignore this. Typically, this case is actually ignored. You just bump up the factor of safety on these, or so Shigley says. The next case is shear of the bolts. This is the most obvious case. The bolts are going to shear off like shown. I guess thinking about it a little bit more carefully, we need to make these bolts a little bit longer. This part here is what we're showing here. But then we've got this outer bracket that it's mounting to, and I probably should have shown those. So we're talking about right now is it's going to be shearing. The bolt's going to be shearing here at this interface. Here, here, and here. That's what has to happen in order for the bolts all to fail and shear. We're going to assume that the load is carried equally across them. So we'll call this C because it's corresponding with this case here. All right, the area of each of these is pi d squared over 4, where d is the major diameter of the bolt, which is 3/8 inch. So that area, 0.110447. Now the shear stress in the bolts, it's going to be a shear stress because these areas, the surface normal to them is this way and this direction. And the load is coming out of the page towards us. So those are perpendicular. We've got a shear stress. Got a shear stress that is whatever the force is divided by 4 times this area. And we know that our yield criterion, we're going to use von Mises. We'd know that according to von Mises, the von Mises stress is equal to the yield strength when the material yields. And if you were to plug our shear, pure shear, into the formula for the von Mises stress, what you'd find is that tau times the square root of 3 is equal to SY. We did this when we talked about welding. So shear stress at yield is SY over root 3. This is about 0.577 times the yield strength. So the yield strength in shear is 0.577 times the yield strength in tension. So this means at yield, we can get up to 0.577 SY. Tau can get up as high as that. The force at yield is such that this is true. We can multiply both sides of the equation by 4a. And this is going to be the force at which the bolts will all yield at the same time. So let's plug in numbers. We've got 0.577. The yield strength that we're talking about here is that of the bolts, because we're talking about yielding the bolts in shear, 92 KSI, times 4 times our area of 0.11. That is 23.452 kips. And these bolts will all yield. Okay, next case. The next case is that the material surrounding the bolts fails. And this looks like a tensile sort of failure, right? Because the area that we're talking about, we're going to be talking about an area here. We're going to be analyzing this area, which we take to be the minimum area that we can find, such that the two parts are going to separate in tension. And the surface normal of those is in the same direction as the applied force. So we're going to have a normal stress here. The relevant diagram for us is this one. We're talking about a failure here on this plane. And the force is being applied like in this direction on the coupler. And so the surface normal is aligned with the force. We've got a normal stress in this area. Now what's that area? That area is this 4 inches, not to be confused with a factor of 4 over here due to the number of bolts, but 4 inches from top to bottom minus 2 holes. And those holes are 17/32. So that's the total amount of distance we have, or length in this direction, times the thickness of them. And the thickness of them is 3/8 of an inch. We saw that these are 3/8 inch thick. And also note that there's 2 of them. They'd both have to separate at the same time. We're going to assume that they carry the load equally between the two. So we're going to have to take that into consideration. But the area is just the area of a single one. This here is 2.9375 inches. Multiplying that by 3/8 inches gives us 1.0156 inches squared is the cross-sectional area that we're talking about. And the normal stress in that area is the force divided by 2 times that area, because we've got 2 of those areas acting at the same time, helping each other out. And we know that at yield, the von Mises stress is equal to the yield strength of the material. For normal stresses, the von Mises stress is just the normal stress. So sigma equals SY at yield. So at yield, the force is equal to 2 times the area times the yield strength of the material. That's 2 times 1.0156 times the yield strength. What's the material that we're talking about here? We're talking about the AZ1018 HR material. That's the stuff that's going to yield here. It's 32 KSI yield strength. That means that that can handle about 70.5 kips. So that's way over designed compared to the bolts. It's not going to separate like that. That is not a reasonable failure mode for this part. E, we're talking about bearing of the rivet on members or bearing of the members on the rivet, or bolt in our case. So the best cross section we can use here is probably this one again. And we're talking about the bolt itself being, up against the side of the hole. In any case, there is a contact stress between the bolt, which is supposed to almost fill up the hole, and the edge of the hole. And so the bolt could yield or the hole could yield. Really, we just need to look at whichever material has the lower yield strength, and it's probably going to be the AZ1018, whatever the steel part is, because the bolt is at grade 5 is heat treated. It's going to be a lot stronger. So we really only have to consider one thing, the one with the lower yield strength. Now, ideally, you would use Hertzian contact theory. You've got a convex cylinder on a concave cylinder, and you've got contact between the two. You can calculate the contact stresses. But as a matter of convention, what we do is we look at the projected area. So we look at this area. And when you look at it from this direction, you see an area that is whatever the thickness, or whatever the diameter of the hole is, that's this distance, this is the diameter, times the thickness of the part. Part here is 3/8. I'll label it T for thickness. We've got 4 of them. We've got 4 of those interfaces where there's going to be that bearing stress. 1, 2 from the side view, but you've got to keep in mind we've got 2 of these things. We've got 4 holes, 2, 3, 4, that are going to be under that bearing load, and we're going to assume that the load is handled equally among them, so just keep that in mind. We're going to calculate the area for just one of these right now. So the area for this thing is just the diameter of the hole. I probably should call this some different letter. This is the diameter of the hole times the thickness that we're talking about. And the diameter of the hole is 17/64. It was a clearance hole. Oops, no, it wasn't 17/64, 17/32. And the thickness was 3/8 inch. 3/8 inch. So that area that we're referring to, the projected area of the bearing contact, 0.1992 inches squared. Now, what kind of stress do we have? Well, the normal to this plane is in this direction, the same direction as the applied load. So we've got a normal stress, and the normal stress value is the force divided by 4. We've got 4 holes times that area. But we know that we yield when F is equal to then 4A times the yield strength. We got 4 times 0.1992 times the yield strength. Which yield strength are we talking about? Well, we're talking about whichever is smaller between the bolt and the part. In our case, the part is what's going to yield first, 32 KSI. That's 25.5 kips. So it looks like the first thing to fail is still going to be the bolts themselves. Now, this is just an approximation. You're probably going to get some local yielding, but it's not going to be some gross yielding. So last thing that we're going to analyze kind of this shear tear out. This tensile tear out is not something that Shigley gives us a way of estimating. You'd have to somehow find whatever the stress perpendicular to this surface is, and that's kind of tricky. So we're just going to analyze this one. And again, I think the best cross section to use is this one here. I'll copy it from above. We're talking about failure at this surface. We underestimate kind of the area. We say, all right, where is the closest distance between the edge of the hole and the edge of the part? So it's going to have to tear here, 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 and here at the same time. And we don't, even though you might think, it would also have to tear here. Well, we don't include that. We're going to be conservative. We're just going to say this distance here. From the edge of the hole to the part, it's got a shear at all these interfaces. And if you look at these from the top down, then what they look like is, I mean, you're going to see 4 of these all in line. Where this here is the thickness, and this dimension here is, well, what is the width of the part, or what is the, what's the distance of the center of the hole, 3/4 inches, minus half the diameter of the hole, 1/2 of 17/32. This distance here is the distance from the center of the hole to the edge of the part minus the hole's radius, half the diameter. This here is almost half an inch. It's 0.484375. So our area is 0.48 times the thickness of 3/8 inch, 0.18164 inches squared. Now we've got 8 of them, right? We've got 4 that we can see here. They would all have to shear simultaneously. We've got 1 on this, or 4 here and 4 here, that all have to shear at the same time. Now, why do I say shear? Because these areas that we're talking about, their normal is in this direction, that's perpendicular to the applied load. So we're analyzing them in shear. The shear stress in them is the force divided by 8 times the area that we have. Now, according to von Missy's criterion, we fail when the force applied is 8 area times 0.577. For the same reason, the yield strength in shear is 0.577 times SY. And which SY are we using? Again, this is the material, this 32 KSI material failing. So we've got 8 times 0.18164.577 times 32 KSI, and I'm getting 26.83 kips. Okay, so the question was, what is the maximum force the bolted joint can support? We didn't put a factor of safety on it. We could, but we didn't. We're just going to say that yield is our criterion for failure. And the maximum force that it can support is the minimum of these 4 forces, right? If we said 70.5 kips, well, then all 3 of these things would fail before we get up to that load. So the minimum of these is the maximum that the thing can support. The bolts are going to shear first. They're going to yield at 23.452 kips. But we had to check all the rest because it's conceivable that, if this distance were a little bit shorter between the center of the hole and the edge, or if the material property, if it weren't 1018 steel, if it were like AZ1006, we'd have much less strength, right? So depending on those things, other parts of the joint could fail before the bolts. But it turns out the bolts fail first. They will yield at 23.452 kips. Other questions that you might see is, you could calculate the factors of safety here. How do you generate a factor of safety? You say, how many times could I increase the von Missy stress before I hit the yield strength? You carry that idea through, and for shear, you're going to find that the factor of safety is equal to 0.577 SY over the shear stress. If you knew the applied load, you could calculate the shear stress, and you could say 0.577 times the yield strength divided by the shear stress. Or if you were in tension and you knew the applied force, then you would simply say SY over the normal stress. And design would just be the inverse process of this, right? You might be asked to size the bolts, and so you'd estimate a size, probably based on just taking a look at the shear strength of the bolts themselves. And then you'd size all the rest of it kind of by eye. Often they encourage that this is at least 1.5 times the diameter of the bolt if you've got the room. That's a rule of thumb that's not going to bother you if it's 1.5 times the diameter of the bolt. Once you've chosen the bolt diameter, you're just going to have to make sure that this material is strong enough to make sure it doesn't yield in bearing stress. If you need to use a weaker material for whatever reason, for manufacturing reasons, then you're going to have to choose a larger bolt diameter maybe. Maybe this is going to govern the design. Or maybe you can choose a clever geometry, right? We have 2 shear planes here, 1, 2, but maybe you could have a third piece in the center, and so you could have more shear planes that would have to fail simultaneously, and that's a way of reducing your stresses. So Design is just the inverse process, involves a little creativity, but you'd probably start by just picking the bolt sizes that are going to work for you and then estimating the rest and then analyzing it to make sure you've got a sufficient factor of safety.